Friends, today we shall continue our study on dynamic equivalence for large scale systems. In the last turn, we have studied the basic concepts of dynamic equivalence. We also studied the different techniques which are used for obtaining the dynamic equivalence. Out of these, the three techniques which we discussed last time, one based upon the distribution factors, another based on the model analysis and order reduction, and the third one was the based upon coherency equivalence. Coherency equivalence is one which is very simple, and it has many merits as compared to the other techniques. First step in the coherency equivalencing is that one is to identify the group of generators which are coherent, and for identifying the group of generators which are coherent, one straightaway approach is that perform a full tangent stability analysis, obtain the swing curves, and group those machines which have identical swing curves into an equivalent one. However, one can use a simplified approach to obtain the swing curves quickly and then identify the coherent group of generators. Now, here the two assumptions on which the simplifications can be made are: number one, that the coherency behavior of the synchronous machines is independent of the magnitude of disturbance, and second is that is independent of the degree of modeling. Whether I represent the system by a simple model or I model the system with details, the coherency behavior does not change. So, from these 2 points actually we can use a simplified approach for identifying the coherent group of generators. From the first consideration that the coherency behavior does not depend upon the magnitude of disturbance, we can make use of linear model. Second is since it does not depend upon the details in which the system is represented, we can use a classical representation of the system or classical model, right, and then obtain the swing curves of the system. We shall discuss the simple algorithm which is used for identifying the coherent group of generators. The linear form of the swing equations is given here. Mi d by dt of delta omega I equal to delta Pmi minus delta Pi minus di delta omega I. This is the one differential equation out of the two differential equations which represent the swing equation of the system. Here delta Pmi is the change in mechanical power of the ith machine, delta Pi is the deviation in mechanical power, delta omega I is the deviation in speed of the machine. Now, here in this equation the speed is represented in per unit. The second equation is d by dt of delta I equal to 2 pi f o delta omega I. Now, in this equation Mi is equal to 2 times Hi. The network can be modeled and we can find out actually the small changes in the network variables or the system variables using this Taylor series expansion. Now, here in this set of equations which I have written here, we are considering the generator internal voltages are represented by the symbol E and the load bus voltage are represented by V. The phase angle of the generator internal voltage is delta and phase angle of load bus voltage is theta. Now, when we represent this generator by classical model, then delta E, that is the change in magnitude of the internal voltage of the generator, is 0, and further assuming that the change in power flow due to change in load bus voltages is also negligible. We can simplify these equations and represent in the simple form like this: delta P delta PL equal to delta P by delta delta, delta P by delta theta, or del PL by del delta L, del PL by delta del theta. That is, these are all the partial derivatives actually with respect to delta and theta. We can write down this equation in a compact form as HGG, HGL, HLG, HLL. This is the matrix. This is the Jacobian of the system. Now, we will make use of the linear differential equations of the system and the simplified network equations. Now, in this model, this change in load power, that is delta PL, will be used to simulate a particular type of disturbance. Okay. Now, the algorithm for identifying the coherent group of generators is to be derived, and the first step is that we integrate the both sides of the differential equations over the integral over the time period delta t minus delta t to t. Therefore, if you integrate both sides of the differential equation, we can write down m I as integral of t minus integral d by dt of delta omega I dt. Similarly, integral of delta p m I dt, integral of delta p I dt minus d I integral of delta omega I dt. Now, the integrals are taken over a time step delta t, that is t minus delta t to t. Now, we integrate and perform this integration function using the trapezoidal rule of integration. When we apply this trapezoidal rule of integration, we get equation in this form, that is m I into delta omega I t minus delta omega I t minus delta t. That is, this integral, right, will be simply integral t minus delta t to t of delta omega I, and therefore, this will be simply m I into delta omega I t minus delta omega I t minus delta t. In this, so far this second term is concerned, or this term is concerned, delta p m I is constant. This term is there to simulate a particular type of fault. Therefore, since delta p m I t is constant, the value of this integral or this term is delta p m I t into delta t. Now, performing this integration and this integration by trapezoidal rule of integration, we get these expressions. Now, in this equation is now an algebraic equation. Similarly, when you perform the integrate similarly when you consider the second equation and integrate this using the trapezoidal rule of integration, then we will get the algebraic equation in this form, that is delta I t minus delta I t minus delta t equal to 2 pi f o into delta omega I t minus delta t plus delta omega I t the whole multiplied by delta t by 2. Now, we have now two algebraic equations. Now, what we do here is that we arrange the equation so that all the terms which are corresponding to time t will be kept on left hand side, and all the terms which are known or corresponding to time t minus delta t will be kept on left hand side. When you make this arrangement of the terms, the first equation is written in the form 1 plus di divided by 2 mi delta t into delta omega I t plus delta t by 2 mi delta p e I t equal to a I t minus delta t. Now, this similarly the second equation is written in this form. That is, on left hand side we have the terms which are corresponding to time t, that is delta omega I t, delta p e I t, delta omega I t, delta delta I t, while on this side the terms are known. Okay. That we represent this right hand side term as a I t minus delta t and b I t minus delta t, where a I t minus delta t is given by this expression which one can derive and satisfy. Similarly, b I t minus delta t is written in this form. Right. Now, the next step is that we eliminate delta omega I t using these equations. That is, you substitute the expression or the value of delta omega I t from this equation in the first equation. When you make this substitution, we get an equation delta p I t equal to c I t minus delta t minus m t I delta I t. That is, we express the deviation in power output of ith generator in terms of a term which is known, that is c I t minus delta t. This is a quantity. The value of c I minus t minus delta t is given by this expression. This is the total expression, that is c I t minus delta t is equal to 2 times m I by delta t, a I t minus delta t plus 2 m I divided by delta t square pi f o multiplied 1 plus d I upon m I. It means all the terms on this side of the expression are known to us. Therefore, c I t minus delta t is known. Similarly, m t I is a quantity which is expressed in terms of known quantity. Now, using this expression and the network model, that is this model, the delta p e, delta p l, Jacobian multiplied by this correction vector, it is in this form. Now, using this model or these equations along with this equation, that is delta p I t equal to c I t minus delta t minus m t I delta I t. What we do is that we replace delta p I t in terms of c I t minus delta t and delta I t. It means basically we are eliminating delta p I t. Now, when you perform this operation, then you can write down the equation in this form: c t minus delta t equal to h g g prime delta t plus h g l delta theta t, where h g g prime is equal to h g g plus m t. Now, here this m t is a diagonal matrix with entries m t 1 1, m t 2 2 and m t n n, depending upon the number of generators. Now, this equation along with this equation, these two equations, the whole we can arrange the two equations in the matrix form. You can write down c of t minus delta t and delta p l t as h g g prime h g l, h l g h l l, delta t and delta theta t. Now, this is the equation which can be solved, because This term is known because this is expressed in terms of the quantities which are corresponding to the previous time step, and this term simulates the type of fault, and therefore, when we solve this equation we get the value of deltas and thetas. Now, this matrix actually is basically a Jacobian, right. The elements of this matrix are constant, elements of this matrix are is a real constant matrix, and therefore, for solving this equation one simple approach is that you perform triangularization of this matrix, that is you perform the triangularization operation of this matrix, and once you perform this triangularization operation, this is to be performed only once because this matrix is constant. Then we can find out the value of the change in angles, right, for in each time step. That is, first I start with time as t equal to 0, then I can get the value corresponding to t equal to delta t, right, and I can iteratively keep on updating the value of these angles delta and theta. Let us now summarize the complete algorithm which is used for obtaining the approximate swing curves. I am using the word approximate because we have made some assumptions. The algorithm is, the first step of the algorithm is you initialize the deltas, omegas and delta p is 0, that is the initial values of all the angles, speeds and delta p. Now, here the angles, speeds and power, they are all deviations from their steady state values, therefore, initial values of these variables will be 0. Is it okay? The next step is increment the time from t minus delta t to t, that is the first step. The third step is set delta PMT, delta PLT according to the disturbance being model. Now, we can consider different type of disturbances. Disturbance may be a 3-phase fault, may be tripping of a transmission line, may be load, sudden change in load at a particular bus, or tripping of generator. All these disturbances can be modeled by appropriately choosing the value of delta PMT and delta PL and making some minor changes in the model. Next step is to compute AIT minus delta t, BIT minus delta t and CIT minus delta t for all values of I. Suppose you have say n generators, right. Then we have how many equations will be there? For each generator we have 2 equations, and therefore, I will be varying from 1 to n, not 2n, 1 to n, because when I take the first differential equation, there is one equation, the constant term is ai t minus t, I 1 to n. Then we solve a set of algebraic equations written here, that is solve the following matrix equations for new bus voltage angles delta theta t and delta delta t. Delta theta t is the change in angle of the bus voltage, while delta delta t is the change in angle of the internal bus voltage or the voltage behind transient reactance. This operation can be performed easily by the process of triangularization of this matrix, where you may not have to invert this matrix, otherwise this large matrix has to be inverted. The process of triangularization will avoid the inversion of this matrix. Now, one small important point is that when you solve these equations, the time step which we have to choose is important, right. Now, for solving these equations, the time step delta t equal to 0.1 second is considered to be quite adequate. Even sometimes you can choose a time step of the order of 0.2 seconds. But however, the study shows that if you take delta t equal to 0.1 second, right, the results will be quite acceptable. However, actually the since we are solving these equations by using the implicit integration technique, and therefore, the problem of numerical instability would not come. The delta t should be kept small to obtain the accurate results from the consideration of accuracy. Now, once we have obtained the deviation in angles, right, we can compute the deviation in generator power delta P E I T can be computed using this equation which was derived earlier. You can compute the expression for deviation in generator power output. And this is expressed in terms of the known quantities, because AIT minus delta t is known, BIT minus delta t is known, that is all the terms which are there on the right hand of this expression are known. Then in case we are interested in knowing the variation of angular speed as a function of time, then we can obtain the value of delta omega I t in terms of the calculated value of delta I t and the known quantity like B I t minus delta t, right. That is, when you come up to the step 7, we have calculated the values of these parameters delta delta, delta omega, delta P E I at time equal to t, right. And since we will be solving this equation for a certain time duration, suppose we want to get the solution for 2 seconds, in the moment the time is equal to the time for which you want to get the solution, you stop, otherwise you go to step 2 where you increment the time step and continue the integration process. That is, step 2 is increment the time from t minus delta t to t, and you continue this process till you get the final solution. Okay. Therefore, the algorithm which we have discussed just now is a simple algorithm which can be used to get the approximate swing curves quickly, right. And then the next step will be that we have to cluster the swing curves together, or we obtain actually the group of generators which have identical swing curves. Now, here we can cluster the generators considering the swing curves corresponding to the bus voltages, or considering the swing curves corresponding to the internal generator voltages. That is, I can cluster or I can examine the swing curves corresponding to bus voltages, that is the delta theta versus t for all the buses, or I can cluster the swing curves using the internal bus voltage angles. Now, in practice, the first step is that instead of clustering with respect to the internal angle, we prefer to first find out the swing curves corresponding to the bus voltages, right, and then the moment we find out that okay, these are the generators where the bus voltages are swing curves are identical, okay, then we form a coherent group. Now, this approach is helpful in network reduction, and once we have done this second step of, that is called network reduction, where we put all the generators on the same bus and then we check whether these generators form a coherent group or not. Generally, it is found actually that when you cluster the cluster or the swing curves corresponding to the bus voltages, then obtain the coherent groups using the delta theta versus t curves, okay. Then it is found actually that the machines are coherent with respect to the internal angle also, okay. Therefore, the clustering algorithm is an important step, and the algorithm goes like this. What we do here is that, suppose you have a group of machines or a set of swing curves which are to be clustered. Therefore, you start actually with one. Let us start with one swing curve and consider that this is the reference curve. Then take the swing curve 2 and compare the swing curve of the second generator with this reference. In case these two swing curves are identical, then the generator 2 belongs to that particular cluster. Otherwise, you put that generator into second cluster. Then we go to the third generator, you compare with cluster 1 and cluster 2. If it belongs to either of the two, you put it there, otherwise you form a third cluster. The algorithm goes simply like this, that delta theta I t minus delta theta r t should be less than equal to Fn, whereas the I is the index, r is the index of the reference swing curve, right. In case this difference is less than a prescribed value over the complete time interval, that is for the complete time interval of say 2 seconds over which the swing curves are obtained, then the generator whose swing curve is corresponding to theta I qualifies to be put in along with reference generator, otherwise you form another cluster. Now, when you perform this step, you will be in a position to put the swing curves in different clusters, and that will give us that these are the groups of generators which form one cluster, this is second cluster, this is third cluster. And once we have identified these groups, we have to go for the next step to find out the equivalent machine. Now, at this stage I would like to give some results of some studies which have been conducted and reported in this important reference. That is, in this reference, which is very important reference paper written by A. J. Germond and R. Padmore, spell is R. Padmore, Dynamic Aggregation of Generating Unit Models, IEEE Transaction on Power Apparatus and Systems, volume PS 97, number 4, July August 1978, pages 1960 and 1969. Now, this is one reference paper which tells us how to aggregate the generator models and obtain an equivalent one. Okay. Now, before that, naturally one has to first perform an exercise to identify the coherent group of generators. The earlier reference paper which I had given, which was written by Padmore, in that reference paper the two case studies have been presented. In the one case study is done for a power system, this is called Michigan system. In this system, the system considered is having 1027 buses, 1027 buses, and the number of generators in this system were 295. There were 295 generators. Now, for this system, the algorithm which we just now described was applied to find out the coherent group of generators. For identifying this, a three-phase fault on a bus was considered. That is, the bus which is considered in this typical system is a 345 kV bus. Okay. The duration of the fault considered in this case is 12 cycles. The duration of fault considered here for this study is 12 cycles on 60 hertz basis. How much time it comes out to be? 12 by 60 seconds, which comes out to be 0.2 second. It's quite a large time. Now, and the swing curves, approximate swing curves are obtained applying the algorithm which we have discussed here, and the results show that these 295 generators can be grouped into a total 50 equivalent generators. That is, when the equivalencing is applied, then these 295 generators can be replaced by 50 equivalent generators. Further, out of this 50, it was seen that 25 groups having only one generator. That is, when you put all the machines into different clusters, what is found was that you can put all the swing curves of the 295 generators into total 50 clusters, and in 24 different clusters it was seen that there is only one generator that belongs, while the other generators were grouped into number of grouped together, or you can easily say 295 minus 25, that is minus 24, not 25. Then this remaining is 271. They were definitely put into only 26 clusters, and therefore each cluster must be having a large number of generators. Therefore, can you see that once you reduce from 295 to 50, then naturally the model dimension is going to reduce significantly. Now, further the time which is required, because the results which are reported in this research paper show that the time which is required to obtain the equivalent is 180 seconds just to get the equivalent, and then once you solve the problem, tangent stability analysis, when you solve using the equivalent, the time required is 55 seconds, while if you solve the complete tangent stability problem, then the time required is something like 341 seconds. Now, we can see actually that the time which is required to get the solution has drastically reduced from 341 second to 55 second. Now, these figures are corresponding to a typical computing system which was used, right. But relative timings will still remain. The second case study which has been reported in this research paper, the system belonged to this WSCC, this Western System Coordination Committee they call it, where the number of generators considered were, or number of buses in the system were 1308 buses. You see this dimension of the problem, 1308 buses, and it had 337 generators, 337 7 generators. For this particular system again a 3-phase fault was considered, 3-phase fault. The duration of fault considered in this particular case is 8 cycles on 60 hertz system, instead of 12 cycle in the previous case, it is 8 cycles. And the time, integration time delta t, which is chosen, is again equal to 8 cycles. Fault duration of 8 cycles, the integration step is also of 8 cycles. And for clustering the swing curves, the tolerance used here is, in the previous case it was 5 degrees, in the present case for the WSSC system, CC system, it is 4 degrees. And when this exercise was performed, right, it could be replaced by 87 equivalent generators. Where the original system had 337 generators, while the equivalent system has now got 87 generators, and out of these 87 generators, the 44 generators or groups, 44 groups were having only one generator. Further, yes, further it was seen actually that these 44 generators which form a group of single generator, they were the generators close to the disturbance, and the same thing was observed for Michigan system also, in the sense actually that the machines which are very close to the disturbance, right, may retain their independent swing curves, while the machines are away, they will behave generally more in a coherent fashion. Okay. Now, the next step for our study will be that we have identified the coherent group of generators. Now, our requirement is that we want to find out the parameters of the equivalent generator. When I say the equivalent generator, means that what is the equivalent inertia constant, what is the equivalent model for the turbine and governors, right, what is the equivalent excitation system for this, because each machine has its own excitation system. We want to find out what is the equivalent of this. Similarly, each generator, synchronous machine, right, we have to find out the equivalent synchronous generator. Similarly, if it is a power system stabilizer, we want to find out the equivalent power system stabilizer, right. Now, this exercise is quite a complex and involved exercise, and I will just tell you today that how do we obtain the equivalent rotor dynamics. First, rotor dynamics, let us see it. Now, the equation or the swing equation for each machine can be written like this: 2 times H I d I delta omega. Here also we can put delta omega I, right, or you can put omega I is equal to omega naught plus delta omega I. Okay. So, that this equation, now when you just look at the definition of coherency, right, all the machines which are coherent, right, the speeds of the rotors, that is delta omega I, the speed deviation will be same for all the rotors, right. And therefore, if I have something like n machines, then I can write these n such equations, okay. Then I add all these equations. Now, since the speed deviation is same for all the machines, right, I can write the equation of the form summation 2 H I for all i's multiplied by d delta omega by dt equal to summation or all I P m I minus summation P E I minus summation d I over I delta omega. Now, I am dropping this subscript I here, right, because all the machines which are forming a coherent group, they have the same speed deviation, and therefore, you can see here that the equivalent machine will have inertia constant which is equal to sum of the inertia constants of all the machines. Similarly, the equivalent damping constant will be equal to the sum of the damping constants of all the machines, and equivalent mechanical input will be sum of all the mechanical input, that is total mechanical input. Similarly, the electrical output is sum of all the electrical output. Therefore, this is one thing which we see, that when I try to find out the rotor dynamics of the equivalent machine, then that equivalent machine has total inertia which is the sum of all the inertias, and similarly the damping that is damping term d I, this the total damping is the sum of damping of individual machines. Now, we will discuss one more important aspect. Suppose we want to find out the equivalent model of the turbine governors, that is each machine has its own turbine and governor, right. Suppose you have a group of machines which form a coherent group. I want to find out the equivalent turbine model, similarly the equivalent governor model. Now, we can write down the transfer function of governor turbine together. Let us say the governor and turbine together. The output of the turbine is going to be change in mechanical power, input is speed deviation, right. Therefore, if I represent the transfer function of ith machine turbine governor G I S, this can be written as change in mechanical power output delta P m I S divided by delta omega I S. That this is the transfer function of ith turbine governor system. Output is mechanical power, input is speed deviation. Now, since all these machines have the same speed deviation, so that I can write down the equivalent mechanical Pm delta Pms as summation G I S summed over all i's multiplied by delta omega I s, delta omega s, or we can drop this I. That is, you can say that the total mechanical power, the equivalent mechanical power can be written as the sum of the transfer functions of the individual individual turbine governor transfer functions. That is, we can say here ultimately that I can just write down here summation or I G I S multiplied by delta omega s. Therefore, now question arises is that how do I find out the equivalent transfer function which will represent the equivalent of all the individual governor turbine transfer functions put together. Obviously, you can see here actually that the equivalent transfer function is the sum of the transfer functions of individual turbine governor models. Okay. Now, here generally what is done is that we come across two type of machines. One is the steam turbine and steam turbine governor, another is hydro turbine and hydro turbine governors. Suppose in your study you find that in one cluster or in group of coherent machines there are few machines which are turbo generators, there are few machines with hydro generators, right. In that case, when we find out the equivalent, we will find out equivalent of all those turbo generators and put by one equivalent machine. We will find out the equivalent for hydro generators and hydro generator governors and put as one machine. We will not combine the hydro machines with the steam turbine driven generators. Okay. Now, just to tell you actually that how do we obtain the equivalent model for this hydro governor, because this model which I have considered here, that is governor turbine model, it can be split into two parts. One is the governor model, another is the turbine model, and when these two models are combined together will give the total model. Therefore, the hydro governor model can be put in the general form as K times, I can use the word G S, G stands for governor, equal to K times 1 plus S times T2 over 1 plus S times T1, 1 plus S times T3 square. This is the general form of the hydro governor model, and the hydro turbine model, if you put it actually GTS, it can be put in the form on 1 plus STW, 1 minus 0.5 TW. This is the model. Okay. Therefore, what is done is that you put these two together, form a equivalent model of the hydro governor and turbine. Then what we are interested is actually that what should be these constants K, T1, T2, T3 and this TW, right, of the equivalent model when we know the transfer functions of individual models, right. The approach will be that what you do is that suppose you want to can say study over a certain frequency range, then you take discrete frequencies, that is you put S equal to j omega I, take some discrete values. For each value of frequency you find out the transfer function of individual models and add them. That is, suppose I want to find out what is the transfer function of say model number 1, it will be G1 S, S equal to j omega. You substitute that value of omega, you can some discrete value. Then this quantity will come out to have actually its magnitude and phase angle. Similarly, second will also have its magnitude, phase angle. Therefore, you can add all this together to form an equivalent magnitude and phase angle at particular frequency. Okay. And therefore, for all discrete frequencies you can perform this exercise. Now, let me define an error function. Equal to summation over all i's G j omega I minus G star j omega I magnitude divided by G of j omega I. Now, this error function represents the numerator of this error function is G of j omega I, that is, this is the transfer function evaluated for discrete frequency omega I, and this is the value of the transfer function of the equivalent turbine generator. The difference will come out to be a complex number. We take the magnitude of this divide by the magnitude of this transfer function G of j omega I for the actual system at the discrete frequency. Then we do this exercise for over the complete range of frequencies and sum of this function. This is defined as error function. Now, our objective is to obtain the parameters of the equivalent turbine governor model, right. The equivalent parameters are the gain constant K, the time constants T 1, T 2, T 3 and T w, right. Now, in order to obtain the parameters of the equivalent generator, what has to be done is that we apply some technique we normally call numerical gradient technique, so that this error function is reduced, and when this error function is reduced and comes to a minimum value, right, that will give us the equivalent turbine governor, time constants and gain setting. Now, if I plot the frequency response of the equivalent turbine generator model and the frequency response of the actual system, right, then these two frequency responses should be identical, right. We can, or I can say that you plot, that is because the body plot magnitude and phase angle, right, and the body plot for the actual system and for the equivalent system, they should match closely, right. That means, we have obtained the parameters of the hydro governor and turbine very accurately. This in case now, instead of having the hydro governor and hydro turbine, if you have a steam governor and steam turbine, right, we can choose the equivalent transfer function of the turbine governor model, right, and performing the same exercise, that is, we define error function and minimize this error function using numerical gradient techniques, and hence obtain the parameters of the equivalent governor and turbine. Okay. Now, let me sum up that today we have discussed an algorithm for identifying a coherent group of generators. Then we have also discussed how to aggregate the rotor dynamics and obtain the equivalent inertia constant of the machine, equivalent damping constant of the machine, right. And we have also obtained we also discussed the method which can be used to obtain the equivalent turbine governor model of the system. Thank you.